Okay, so next up we have Alex Klenner. He's currently at Fraunhofer working on extracting chemical information from patents, but he comes from a background of computer-aided drug design and bioinformatics. He has an almost degree from the Swiss Federal Institute of Technology in Zurich, and where he's been working on virtual screening and drug design using fuzziness and self-organization.
So we are having a project at Fraunhofer. It's called UIMA HPC. And we're also dealing with exploring and visualization of chemistry and patents. The outline, we will see some of the challenges and the motivation why we are dealing with patents, but we have heard a lot of this already. I will show you some of the exploration tools, and I won't go into the details of the problems we are running into. These are pretty much the same problems everybody here in this room is running into. I will introduce you our workflow based on UIMA and UNICORE. And then I will show you the visualization. This is where ChemAxon in our workflow comes into play, actually. And we are able to recreate the PDF with enriched information, pretty much similar to what we have seen before. And we are using Instant JChem to collect all the chemistry data and to present to the user at the end. So the challenge, we have already learned about bigger numbers in the Marcouche forum. This number comes from the European Patent Office. It's about 470,000 chemistry patents classified as chemistry. And these patents contain chemical knowledge of 10 decades and more. So there's a lot of information in those patents. And one problem with these patents is that they have multimodal information. We have also learned this before. They have images and they have text, and we need to extract both information. Not only the text, not only the images, but we need the combination of both and the co-reference between those informations. The information is not easily UIMA accessible because of the sheer amount of data we are dealing with. It's mostly unstructured. A lot of the PDFs are not OCR'd so far, especially the old ones are just TIFF images. We have learned about chemical noise already yesterday, and that's also a problem. We have to deal with different languages, and as I said, they are not searchable. And maybe the difference in our approach is that we are offering an on-demand service where you can just send a collection of documents and you will get the results, which are processed with a tool, with tools that you can choose from a box of tools, from a toolbox, so to say, here. So the exploration task is in 3 steps. We have a pre-processing task. That is where we're separating the image and the text data, even though it's only image as a whole. So it's a TIFF image PDF. This is done with ChemoCR. This is our in-house tool for structure converting image to structure. And we are also dealing with tables at the moment. So we have trained this program also to separate the tables, the images, and the text, but we are not able to process the tables at the moment. Then we are doing an optical character recognition. We have tried with Abby Fine Reader, but now we have switched to Tesseract. This is open source from Google, and it works pretty good. After these 2 steps, there comes the processing. This is where we do our chemical named entity recognition. We are using different open source tools and also some in-house tools. We are doing patent zoning also, so we want to identify regions of the patent where synthesis information is stored, or where claims are stored and description. And in the post-processing step, we want to try to solve the co-reference problem, and I will show you what we mean with this in a second slide. Yeah, this is the output from ChemoCR if you visualize it. So it tries to identify the chemistry in the patent, and the red areas actually are chemistry classified by ChemoCR. The green areas contain text information, and the blue areas don't have to be considered because they contain no information at all. It's just blank spots. And what we mean with co-reference solution is, for example, that these structures are referenced by Roman 1 here, and this Roman 1 will appear in the text. And in a 400 pages document, it's quite hard to figure out which structure belongs to which number, and we want to provide a system that easily makes this information available. Yeah, this is the OCR part. And in the OCR part, you can see the page is already, we got rid of the image information, so we can deal with the OCR separately only on a text basis. And for us, it's important that the OCR actually keeps the formatting of the text. This is important for the zoning part, because having paragraph information, heading information, helps a lot with the zoning. For chemical named entity recognition, we are using Linda. That's a machine learning module developed at Fraunhofer. It's a conditional random field trained for UPAC terms. Then we have our in-house ProMiner. That's a dictionary-based approach for tagging chemistry names or drug names or gene names, for example. We're also using OSCAR, and we are actually, I missed to put OPSIN here on this slide because we use OPSIN as a name-to-structure converter. For zoning, we have our in-house synthesis classifier. This is a rule-based system. And we have a claims and description tagger, which is also rule-based. The workflow, we are using the UIMA framework. This was formerly developed by IBM and is now under Apache license. It stands for Unstructured Information Management Architecture. And basically, UIMA consists of 3 parts, every UIMA workflow. So you have the collection reader that converts any document that you provide into the internal format, which is called CAS. That's the Common Analysis Structure. Then you have multiple analysis engines that actually do the work. That can be OCR, annotating, or zoning, or something like this. And at the end, you have a consumer. And here you can see an example workflow. You have a PDF document. A collection reader is converting the document into the CAS object. And then you have an implicit parallelization provided by the UIMA framework. So every analysis engine can be instantiated as many times as you want. You can specify this like a hard integer number, or you can just say, take as many cores as available. And the consumer writes the annotated data back into a format that you can read or access. And in this case, that would be the Instant JChem database. And this is a more complex workflow. So we try to provide as many collection readers as possible so that you can process a lot of different documents. PDF, TXT, Word documents. You can also read from a MySQL database if you want. Then we create a pool of CAS objects. This is actually done by the UIMA framework. The analysis engines draw CAS objects from this pool, process them in parallel, and the different the different consumers write different output formats. For example, the Instant JChem database, or back to the PDF, to the original PDF with enriched information. Or you can also have a look at the XMI. This is the serialized CAS object from the UIMA framework. So we are combining this architecture with UNICORE. And UNICORE is made to access grid resources. UNICORE provides safe communications through certificates. So the information is sent encrypted between server and client. UNICORE provides us with an outer parallelization in combination with our inner parallelization from UIMA, so the workflow can be duplicated. This is done automatically, so you don't have to care. This is decided depending on the input size of the data. We have a scheduling system from UNICORE that checks if cores are available and if enough cores are available. And UNICORE brings the rich client, which is the graphical user interface that has drag and drop functionality, very similar to KNIME. So you can just put the different grid beans. These are the names of the different analysis engines there. You can just drag and drop them into the interface, and then you can start the job by clicking one button. Also, the UNICORE Rich client allows, if you once have connected to the grid, the automatically download of all the grid applications that are available. It also brings the CAS editor, so you can inspect every step of the processing. You can download the CAS and have a look at the annotations. And there is a web interface in development so that you can start your jobs from a web service. This is how the UNICORE Rich client looks like. And for those of you who know KNIME or Pipeline Pilot, this may look familiar. We have already seen a slide in David's presentation where he showed some KNIME nodes. And this is very similar. We have different collection readers here in green. The analysis engines are shown in blue. So there we have classical natural language processing tools implemented for the OpenNLP suite. We have our ProMiners that do different tagging based on a dictionary. And we have different writers. For example, XMI back to PDF, or here in a format that can be read by Instant JChem. And you can just drag and drop those. You can define the control flow and then press the green button in the top, and the thing is sent to the grid and processed. So this is a PDF created with the PDF writer. We also have this functionality that we can highlight the terms that were identified. And you can see here that the highlighting does not correspond to the actual text. This is because we have to OCR the text, and then the text is laid behind the original picture, and sometimes this alignment doesn't work 100%. And the actual highlighting is highlighting the text in the background, but it works still okay. And you can click this highlighting, and such a picture will pop up. This is created with Marvin, or with JChem, the API. And what you have here are link outs to ChemSpider and Pubmed. You can click those, and you will get additional information to the molecule you have in this pop-up. And we do one additional thing with the PDF. Now, this is the PDF shown in the Adobe PDF viewer. We also create bookmarks that allow you to jump into the structure directly. You can see here it's the InChI, but you could put anything here to normalize the structures, and then you have the actual structure found here with the page number. And if you click it, you will directly jump to the page in the PDF. And yeah, so this is all normal PDF functionality. You don't have to use a special viewer or something. This can be done in Adobe PDF viewer. The second writer I showed you in this workflow was the Instant JChem writer, and we have seen a lot of those pictures. The Instant JChem writer just will give you an output that allows to inspect all the molecules. If you processed a whole collection of different molecules, some Word documents, some PDFs, some text, you will have an overview of all the molecules found. You will also have an URL field, which is not shown here. You have the name of the original PDF here. And whenever your PDFs are stored are hosted as a web service, you can use the URL field to directly jump to the page where the actual entity was found. Because this is also something that is supported by Adobe. You can have a HTTP header request jumping directly to the page. Yeah, this is also something we support. And of course, you can have a lot of additional information in this JChem database, Instant JChem database. So I'm already at the end of my presentation. We are dealing with a UIMA framework, and we try to stay in the UIMA framework. It's an active growing community. There's a very active mailing list. There are a lot of freely available UIMA components, and we can easily plug all of them into our workflows. We have implicit parallelization for large-scale applications. So our typical use case is that we get a set of documents, and they have to be processed as fast as possible. We have this intuitive drag-and-drop workflow creation, as shown before. We can support various output formats, for example, the Instant JChem format or MySQL, or we can write an RDF triple store using URIs. It's easy to integrate third-party software in existing workflows. And so if you're interested to see your software there, it's pretty much done already. And yeah, my acknowledgments, of course, my colleagues at Fraunhofer, Max Zimmermann, Carina Haupt, Ludwig Wildner. He's a diploma student doing all the conversion from chemo-CR to UIMA. Jülich, those are our partners providing the actual grid architecture. And Sebastian Demuth is developing the UNICORE client. Taros, our chemical advisors and patent annotators. And Scapus, they are developing the business plan. And the whole project is funded by the Federal Ministry of Education and Research. And thank you. Oh, sorry, one addition. There's one last slide. You may find this one on your stick. This won't work because our IT wasn't sure if the Glassfish server we need for this is secure enough. But they are working on this, and this will go live hopefully very soon. So if you are interested in having a demo, you can either send me a document, or we can try it here in the break or something like this until this demo goes online. OK, thank you.
So help me understand what we started with the tables here. Yeah. The general concept here that I want to ask about is how do we connect data from different parts of the document together? So the structure on page 2 with the comment on page 10. Can you just tell me?
Yeah, this is done.
It came up earlier on tables, but just how do we connect the different pieces?
To understand this, you have to go a little bit deeper into the UIMA framework. So every CAS object stores different views onto the data. We have a document view, which stores the text, and we have an image view that stores the image data. And then you define annotation types, and we have one type. This is called relation. And in this relation, we can store 2 different entities one image and one text entity. So every time we found this Roman 2, we will store the corresponding image information there and vice versa. And then you, of course, need a good presentation or a good output format to visualize this. But we are having, at the moment, we are working in the CAS editor. We're providing an image view. And then you have the PDF on the left side, the original image, and the text view where the extracted text is on the right side. And you have all the relations between those. And now we are still working on having a good visualization of what belongs to what, but we haven't solved this